So it's a great pleasure to have David Johnson here. He is the author of the Bible of NP-Completeness, which is really the thing that allowed computer science to move forward despite having lots of hard problems we couldn't solve. At least we found a way of dealing with them. He has also kept working on the NP-Completeness problem and general algorithms to keep trying to update us and understand what are these problems that we cannot handle. He has been my boss at AT&T for 14 years. And we know each other pretty well. I'm used to going to him whenever I need something, so I have to stop that. But anyhow, welcome to David.
Thank you. I went to Mikkel a lot when I did things too. This is the book Mikkel mentioned. And it's why I'm connected to NP-Completeness. It's been in print for 35 years, and it's still a bestseller. It's number 187,000. but that's not the impressive thing. It's this. For books in Now, I really don't deserve a lot of credit for NP-Completeness because it's these people who came up with the original idea. Stephen Cook, Landon Levin, and Richard Karp. Cook and Levin invented the concept of NP-Completeness contemporaneously, independently. Published in Cook's paper in 1971, and Levin had a paper, a one-page paper in Russian in 1973, but that was long after he'd been talking about his results in the Soviet Union. And Richard Karp was the first to illustrate the breadth and applicability of the concept. He had a paper in 1972 at a conference at IBM where he presented a list of 20 plus problems that were NP-complete, some of the most famous ones. I'm famous for the book, but probably most of the cartoons in the book. Suppose, so I'm going to explain it, since for those of you who aren't familiar with it, forgotten. Suppose you are a fresh graduate from this university, and you go to work in industry. And your first assignment to the boss is design an optical bandage. And he tells you what bandage that is, different definitions, and you go back to you get all your textbooks and you work and you work, and you can't figure out how to do this. And you're stuck, and you do not want to have to go back to your office, back to your boss's office, and say, I can't solve it, I guess I'm just too dumb. What you'd like to be able to say is, I can't solve it because no solution exists. You can't, NP-Completeness doesn't allow you to say this. What NP-Completeness allows you to say is, I can't solve it, neither can all these famous people. So, some definitions. P is a set of decision problems, problems with an answer that's either yes or no, that can be solved in polynomial time. And polynomial is any of these things up to n to the 20 million, etc. NP is a set of decision problems such that if the answer is yes, there exists a short proof of that fact that can be verified in polynomial time. And let me illustrate that concept with a couple of classical problems. Satisfiability. In this problem, you're given a logical expression in conjunctive normal form. For instance, x or not y or z, and not z or y or not x, and y or not z or not x. You want to find the assignment of truth values to these variables so that this is true, that each of the clauses, each of the clauses is true, and all of the clauses, all of them are true. The question is the expression satisfiable? Is there an assignment of true or false to the variables such that all the clauses are true? In this case, the answer is yes. For instance, one satisfying truth assignment is x equals true, which satisfies the first, y equals true, which satisfies the second, and z equals true. Well, y equals true will satisfy both the second and third, so everything's satisfied. And that proof can certainly be verified in following time, just to check that all the clauses are satisfied. So this problem is an NP. Another example is the traveling salesman problem, which I talked about on Wednesday. In this, you're given a set of cities, and for each pair of cities, just an integer distance between. And you're looking for a permutation of cities that minimizes the total length of a tour which a salesman would take, starting at the first city in the permutation, going to the next, and then wrapping around back to the first city. So you're visiting all the cities in the cycle. You want to find the shortest cycle of this sort. Now that isn't an NP, that's an optimization problem, but there's a clearly closely related decision problem. Given an integer k and a TSP instance, is there a tour of length k or less? And I'll leave as an exercise to show that if you could solve this problem, clearly if you can solve this problem, you can solve this problem. I'll leave as an exercise, if you can solve this problem in following time, you can solve this problem in following time. With equivalent versions of the decision problem. So NP-Completeness, well, let's start. Observation. P is contained in NP. Because if you can solve it, your short proof is just to run your algorithm and solve it. An empirical observation is that there are thousands of well-known, well-studied problems that are in NP, but not known to be NP. And people have been working on it for a long time. This is all people in a long line of people in part two. And they haven't been able to solve these problems, so they're happy to conjecture that P is not equal to NP. And so a behavioral definition of NP-completeness is the NP-complete problems are in NP, the ones in NP that can only be in P if P equals NP. So if this problem were in P, then NP would equal P. And since we don't believe that, that suggests that this problem is hard. That's sort of a behavioral definition. I'm going to get to the technical definitions shortly for those who like technical definitions. So an early open problem, how do we formally define and name this class? I've just given you sort of this NP-complete class. I gave you this informal definition. And so an open problem that puzzled the community back in the early 70s was how are we going to define precisely and what name are we going to give it? This is the first of the open problems. So why NP-completeness? Why the name? Well, first some terminology. And some history of terminology. The idea that the class of problems solvable at following time was a useful subject for study was first formulated by Cobham and Edmonds in the mid-60s. And here are pictures of Cobham and Edmonds more recently. And the idea of NP was formulated by Edmonds in the same year, a different paper. He actually he thought of it as a good characterization. I just talked to him last week at a Dynamics workshop and said, well, a good characterization for me wasn't just NP, it was NP intersect co-NP. Co-NP is the problems where it's easy to prove a no answer. So if you take a problem in NP and reverse the answers, you get a problem co-NP. And so he thought a good characterization is if you had a short proof of both yes and no answers. But that included the idea that we now become NP. And since I've just shown you pictures, I should show you another picture, and I'll give you a picture of Edmonds a little closer to when he proved the result. So here's, and these first things we're talking about decision problems, we're talking about Edmonds and Cobham and all those, we're thinking about problems that had answers, functional problems. So FP was the things that you could solve at following time, and FFP was the things that had good characterizations. Cook made the useful restriction, this is Cook's paper, this is an NP-Completeness paper, made the useful restriction to decision problems, or languages. Language is, string is in a language. Is a string language a decision problem? You can sort of make correspondence there. And define the classes P and NP without giving them names. So P would then be FP restricted decision problems, and NP is NP restricted decision problems. So those are the classes that Cook talked about. When he talked about NP-completeness, he was talking about problems complete for NP under what we now call polynomial time Turing reduction. So to relate problems, he used the Turing reduction, which goes as one of the reductions goes as follows. A reduces to B if problem A can be solved in polynomial time when we're given a subroutine for solving B that returns an answer in constant time. So with a polynomial calls to the algorithm for B, I can solve A. So the NP problem in that sense would be here. In NP, but not in P, assuming that P is not equal to NP. Karp took things further. He introduced the named P and NP, and observed that Cook's theorem still holds if we use an even simpler notice of reduction, which we now call a polynomial transformation. And now A transforms to B. If given an instance x of A, we can in polynomial time construct a single instance f of x of B, such that the answer for x is yes, if and only if the answer for f of x is yes. And so his definitive NP probably might be a little smaller because it was a stronger kind of reduction. But that's how he, and he didn't have the name of NP-Complete. He did not provide a name for the class, but subsequently several other people had suggestions. So here's Cook's class. What Karp said was polynomial complete problems. Grammarians observed that it's really supposed to be an adverb, so it's a polynomially complete problem. Levin called them universal sequential search problems, not problems. But that referred to the larger class consisting of all sorts of problems to which SAT can be reduced in polynomial time to Turing reductions, and which in turn could be, so they're equivalent to SAT. We have reductions both ways. That was Levin's notion. And so that's a bigger class. And Sai called them P-complete problems, which referred essentially to Levin's class. So these names were floating around, and we got NP-Completeness thanks to yet another light in computer science, Donald Knuth. Here's a picture of Donald Knuth, Mike Gary, and a much younger, hairier David Johnson. So in 1974, Knuth wanted a better term than at least as hard as the polynomial complete problems to use in volume 4, which now at least has begun coming out. Volume 4A of the art of computer programming. And he privately circulated a poll and reported the results in an article called The Terminological Proposal in SIGAC News in 1974. He was interested in the bigger class. All the problems were at least as hard as the NP problems. In his poll, he rejected the term P-hard, which was Sani's proposal, for semantic reasons, because if P equals NP, the problems would be much, if P did not equal NP, then it would probably be much harder than P, so that seemed the right term. And he came up with what he thought were 3 very good proposals: Herculean, formidable, and arduous. And he tried them out, and various of his colleagues tried them out in courses, and were leaning toward one. I can't forget which one. Depending on the day, they choose a different one. But so he went out, sent out the poll, and the result was no winner. Nobody who got the poll liked any of those terms, as you might suspect. But fortunately, he asked for writing notes. And some of them, more entertaining, were the following. The hard-boiled problems in honor of Cook. The hard-asked problems, hard as satisfied Cook. And my favorite Shenlin's the pet problems. They were his favorite problems. Currently, they were probably exponential time. If it turned out that P does not equal NP, they would be provably exponential time. And if it turned out that P equals NP, they would be previously exponential. The right and winner was proposed by a variety of people, including a bunch of us at Bell Labs, and that was NP-Complete for the problems complete for NP under polynomial transformations. And NP-hard for problems to which SAT reduces using polynomial Turing reduction. So that was the class that Knuth wanted. So NP-hard was the term that Knuth wanted. Advantages of this. Well, it suggests to the reader that this is a well-defined technical concept, which Herculean would. And it's consistent with standard languages and standard language for recursion theory. And it's relatively easy to explain, which hasn't kept reporters from regularly getting it wrong. Disadvantage, of course, it does require explanation. And although in this case one would resort to Albert Meyer's short calculation, which I stole from and used in some of my earlier papers, a class of problems notorious for their computational intractability. So there's still a missing name. That's Levin's, we have NP-complete problems, we have NP-hard problems, and in Levin's class. And in our book, we propose, and nobody's ever adopted, NP-equivalent for those problems. So if you'd like to have a name for that class, please use this. So that's the first one. The second open problem is open problems about problems. And this is more probably what you expect from the abstract. In our book, we had a list, appendix 13, of open problems, which we didn't know were either problem time solvable or NP-hard. In the 35 years since it appeared, all but 2 of them have been resolved. In fact, half of the 10 that resolved, half turned out to be P and half turned out to be complete, showing that we were even-handed in our choice of the list. And I'll talk about several of these. So one of the things that turned out to be NP-hard is chordal graph completion. You're given a graph, an integer k, and you ask, is there a superset of the edges that has at most k edges to your original graph, such that the resulting graph is chordal. In other words, every simple cycle of more than 3 vertices, there is a chord, an edge between 2 non-adjacent vertices of that cycle. So there's a chord. There's a chord. Adding those in, I now have a chordal graph. And this corresponds to the problem of minimizing the fill-in when performing Gaussian elimination. So it actually has an application. And it was proved NP-complete by Mihaly Janakakis, my colleague at Columbia now, in 1981. One of the ones that's proved to be a problem of time is the spanning tree parity problem. Here are given a graph on a partition of the edges into sets of size 2, disjoint sets of size 2. And you ask, is there a spanning tree such that each of these sets is either both in the spanning tree or both out of the spanning tree? So this shows that there is such a spanning tree for this graph. You have both green edges, both red edges, and brown edges. And this turns out there's a general problem, a matroid parity problem. This is a special case. In most of the other special cases, the general problem is NP-hard. Most of the other special cases were known to be in P. This is one that was left open. And Lovaas showed that in fact it's in P2. So for the other ones, here are the people who resolved them and the dates. And you'll notice that most everything was resolved by 1989, early 89, and then we had a big gap until 2004 when the famous Agarwal, Kyle, and Saxena proved that primarily testing was in P. We knew they had a good characterization in Edmund's sense. It was both an NP and co-NP. So it was NP intersect co-NP, and they showed that it was in fact P. And even more recently, minimum weight triangulation was proved to be NP-hard. Now that problem, I'm a little embarrassed about. The problem is you're given a collection of points in the plane, and we want triangulation, a set of edges that turns it, breaks it into triangles, breaks the convex hull of points into triangles. And we take, to make this something that is computable, we're going to take discrete Euclidean distance, which is take the Euclidean distance rounded up, so it's an integer. So there's a triangulation. And the problem was that's NP-hard, but is that the right metric? Why would anybody care about the minimum weight triangulation? Typically, triangulations are used in numerical analysis for getting things for which you can use your numerical computations. And for that, you want different things. And they're all solvable in polynomial time. If you want to maximize the minimum internal rectangle of any of the triangles, maximum angle, minimize the maximum aspect ratio, or minimize the maximum edge length, all of those are polynomial time. But we have to pick the one version that was NP-hard, and probably nobody cares about. And I'm fine. So, now those, there were also, after the book came out for several years, and actually continuing until now, roughly, I've been writing a column about it, an ongoing guide. First in the Journal of Algorithms, then a long gap, and then the ASM transactions algorithms, and now I'm in the middle of another long gap. But I hope to get back to it. And in those columns, I would occasionally pose new open problems, and some of them were quite important problems and have been resolved. So let me mention a couple of those. Imperfect graph. A graph is perfect if for every subgraph, every induced subgraph, the maximum complete size equals the chromatic number. So it's imperfect if there's a subset of the vertices, such as the subgraph would be induced by a subset, has a chromatic number larger than its maximum clique. Chromatic number is the number of colors you need to assign the vertices so that no two adjacent vertices get the same color. So it's at least the size of the maximum clique, which is the graph where every vertex can every one. So, perfect graphs, all the subgraphs have an equal. And if imperfect, you could have some subgraphs where the chromatic number is bigger. And on the membership, the fact is that NP is not immediately obvious, and proof requires the ellipse and it was not known to be NP in NP. It's now known to be NP as a consequence of the perfect graph theorem and an algorithm which says that the graph is perfect if and only if it does not contain an odd hole, and then an algorithm for looking for odd holes. An odd hole is one of these cycles of an odd length with no chords. That's an odd hole. So these two impressive long papers by a bunch of people, Robertson, Chinovsky, Seymour, and others. I can't pronounce. Now here's one that turned out generally complete too, and also has interesting applications. Even cover. A collection C of subsets of a given finite set X and a positive integer K, and you want to know, is there a non-empty subcollection of size K or less, such that each element of X is in an even number, possibly 0, of the sets from C prime. Now, if you took an empty set, then everybody being 0, they'd all be an even number. But you have to have at least one of these sets in your collection, and one element on each. And that's a combinatorial restatement of the classic problem from coding theory that asks whether the minimum weight of a non-zero code word in a binary linear code is K or less. That was proved at NP-hard by Vardy in 1997. One more, shortest vector in a lattice, collection of vectors, each a member with rational entries, and integer B, and you want to know, is there a non-zero vector A in Z to the n such that if you sum up A times, take the linear combination of coefficients A, you'll get a vector of length B or less. This is NP-complete under a slightly definition under randomized reductions. So it's, it can be solved in random polynomial time if and only if NP is contained in random polynomial time. These are sort of analogs for deterministic polynomial time, which are allowed to coins. This has the difficulty of this problem has there are cryptosystems based on the assumption of this problem. So this helps support those. My most embarrassing open problems from the column resulted from the one where I talked about NP-hard graph problems and included a table where I listed a whole bunch of problems, a whole bunch of classes of graphs, and a bunch of problems, and what I knew about the status of that problem for that class. And of course, when you make a table like this, there are lots of holes which aren't resolved. And after this, many papers appeared saying, on an open problem, Johnson. And now some open problems, if you want to work on some open problems, they're still open after all these years. Well, there are two from the original list. There's graph isomorphism. Given two graphs, is there a one-to-one function, one-to-one onto function from one versus one another, such that if UV is an edge, then the image in the first one, and then the image is an edge in the second one. Now that is unlikely to be complete because if it is, then a structure called the polynomial hierarchy collapses, which is built on, it's a hierarchy built on P and NP as the lowest levels, and getting harder and harder by having oracles to earlier things. And nobody thinks that collapses, but if this is NP hardware, it does collapse. Precedence-constrained three-process scheduling, which is perhaps the one that it might be most accessible, although I worked on it, Mike, Gary, and a bunch of others worked on it many years, made the progress. It was claimed to be in polynomial time by Ernst Mayr about 30 years ago, but the paper didn't come out then. He never had it proved. So you're given a set of unit-length tasks and a partial order on the tasks and a deadline. And you want to schedule the tasks on three processes so as to satisfy the precedence constraint, so that if a given task, if T precedes T prime, then the task T has to finish before T prime starts. And you want to do this on three processes. So here would be a schedule. 1, 7, and 4 all have no predecessors, and so they can go the first thing. And this is schedule length 4. So that's what you want to find the shortest, find it, given a K, whether you can get a schedule that. No, now here's some open problems that weren't in the book, but are very important. Factor. If we could factor in polynomial time, we'd break a lot of crypto systems, and internet commerce would be in real trouble. So we're given integers and k less than equal to n, and you wonder, does n have a factor f, not trivial factor less than equal to k? So if you could solve this problem in polynomial time, you could factor in polynomial time. You just you do binary search to find the first factor and divide it out and keep going. And the problem is that n intersect co-NP. It has a good characterization in Edmond's sense, because the unique prime decomposition of n provides a short proof of both a yes and a no answer. And you could verify that a supposed prime decomposition is true. Well, now you can do it simply by using the polynomial time algorithm from Kyle, Saxena, et al. For primality testing. But it was known to be an NP even before that, because you could present short proofs that each prime is a prime, in addition to this, and you could have a verification that was the prime decomposition. Again, since it's NP is a co-NP, if then we complete the polynomial time hierarchy collapses. So it may be hard, but we don't think it's NP complete. And finally, what you may not have heard of, graceful graph. You're given a graph, an integer k, and you wonder, is there a one-to-one function of, from the vertices to the integers from 1 to k, such that you get distinct values for the absolute value of the numbers assigned to the endpoints for all edges. So no two edges get the same difference. And if the answer is yes, for k equal to the number of edges, then the graph is called graceful. Surprisingly, this actually has applications, or at least the paper that claims it has applications. The Kutzig-Ringel conjecture is every tree is graceful, and it's been verified computationally for all trees with up to 35 vertices. But whether it's NP hard or not, for general graph, is still open. Okay, now the biggest remaining open problem. Anybody have an idea what the biggest remaining open problem is?
Well, like P is equal to 100.
Very good. The solution is worth $1 million. The Clay Institute, it's one of the Millennium Prize. There were originally 7. One is the Poincare conjecture has been solved, but it's one of the 6 remaining open problems that they're offering $1 million for. And many think it's the most important of those problems. Many people have been, as to what people think about it, besides that it would be a lot of money to solve it. Bill Kassarch has 10 years apart, conducted a poll of the theoreticians as to what they believed. And here are the results of 2 polls. In the 10 years, we've got more respondents, and the number of people believing P is not going to be increased substantially, whereas the number of people believing they were equal stayed the same. Now, if you look at these things, what happened is a lot of people who claimed they didn't know in 2002 decided that they're not equal. And 63% thought the problem would still be unresolved in 2100. And there's a belief that they're not equal, and it's very hard to prove. Several thought it would take the serious mathematics outside of computer science fields, such as Ketton-Mulmuley has a proposed approach based on algebraic geometry, which some people think is interesting. He's got an approach with arguments that are just at the first of many, many steps that would make that approach work. And again, we had some comments. So Richard Karp believes intuitively that they're not equal when it's only an intuition. Boaz Barak said, I'm almost certain that P is not equal to NP. I tend to agree with Scott Aronson that given all the evidence for it in other fields such as physics, P does not equal to NP would already declare the law of nature. Richard Lipton said P equals NP will be proved on December 12th. Don Knuth was recently asked this question. He, in honor of the electronic versions of his Art of Computer Programming volumes, he answered 20 questions, and one of them bore on this question. And his response was, I've come to believe that P equals NP. My main point, however, is that I don't believe that the equality will turn out to be helpful, even if it is proved, because such a proof will almost surely be non-constructible. Although I think an O of n to the capital N algorithm for some fixed m probably exists, I also think human beings will never know the value of n. I even suspect that nobody will even know under bound on it. And then finally, Jack Edmonds is so confirmed in his opinion that he's put it on a boulder in his front yard. NP is not equal to NP in second P, but everything that has a good characterization in his sense is actually probably not solved. And if you want to keep up with the status, Gerhard Boginger keeps a webpage listing all the results of people proving or disproving it, and P versus NP that he knows of. There are now 106. My reason, 53 for equals, 45 for not equals, 1 for both. 3 for unprovable and decidable, 1 for NP equals co-NP, and 3 others. He writes it, everyone he takes states its base value because he just says they prove this or they prove that. The first entry is rather famous. It's due to Ted Swart. It's the one that led to the only published paper from this list. What Ted said, he wrote a number of papers, some of them having the title P equals NP, in which he gave a linear programming formulation of polynomials for the Hamiltonian cycle problem. The Hamiltonian cycle, given a graph, is there a cycle, is this all the vertices? So it's closely related to the TSP. Since linear programming is now known to be polynomial solvable, and the Hamiltonian cycle problem is NP-complete, he deduced that P equals NP. In 1988, Mihalis Yannakakis, when asked to referee this paper, went further and closed the discussion completely by writing a paper that said that expressing combinatorial optimization problems by linear programming, that to do the TSP with a symmetric linear program required exponential size. So the TSP is essentially the TSP polytope, the convex hull of all the tours. For the tour, if you take a if you have n cities, take n squared dimensional space with a vertex for each tour, representing a set of edges in the tour. And take a convex hull, that's the TSP polytope. And you cannot describe that polytope by a symmetric linear program unless an exponential number of variables plus constraints. Recently, this was extended to asymmetric LPs. because people Swart then tried to get around models of the result by doing asymmetric formulation. And so one might think this is a good way to perhaps prove P does not NP by showing these polyhedral results. Unfortunately, Thomas Rothfuss added perfect matchings to have this problem. So there's a problem that has polymer-time algorithms whose polytope cannot be described by a linear programmer. Now, my favorite P equals NP proof. I'll give you my favorite of both. Observation 1. Satisfying problems NP complete for instances in conjunctive normal form, like we've seen. Observation 2. Here is a linear time algorithm for solving instances of satisfiability in disjunctive normal form. So you want to satisfy a disjunctive. You just have to solve one of these clauses. Now, the standard scheme for proving P is not equal to P is as follows. Problem A is NP hard. Any algorithm that solves A must use technique X. Any algorithm that uses technique X must take exponential time. Major open problem. How to convince people who use this scheme that they really have to prove 2? We've been talking about open problems about problems. This problem X can be hard. That was a popular word for many years, but that's sort of been supplanted in at least the theoretical community. Today the question is, how good can an approximation algorithm be for problem X? Assume P is not. So this brings me to the lost cartoon. When we wrote the book, I actually had a fourth cartoon to be used in chapter 6, but my co-author, perhaps wisely, vetoed the exclusion of this cartoon. We may not be able to solve it, but we sure can get close. So there are various levels of approximation. You can get a bound. These are algorithms that polynomial algorithms can actually do as far as getting close. You can get a bounded difference. So chromatic index. Is that if you take a graph and you want to color the edges so that no two edges that share a common endpoint have the same color, well, you can get with finding the chromatic index is NP hard. That was one of our open problems with Jerry Johnson. But you can get one more than that easily with polynomial time. In fact, I think if you think about it, you can come up with the algorithm while I'm talking. You get sublinear differences, or asymptotic optimality, where you get an algorithm that is optimal plus a little low optimal. And the classic example of that is bin packing. In bin packing, this is the paper problem I wrote my thesis on. You're given a collection of items of sizes between 0 and 1. And you want to partition them into groups of total size, each group having total size at most 1. So you could put each group into a bin of size, a unit capacity bin. And you want to use a minimum number of unit capacity bins. And for that problem, you can get optimal plus log squared optimal, which is recently, you could also, and so the next step would be fully polynomial time approximation schemes, where for any epsilon, you can get within a factor of 1 plus epsilon of optimal in time polynomial the size of the instance and 1 over epsilon. Then there are knapsack problem. Then there are non-fully polynomial time approximation schemes, where the running time is now polynomial for any fixed epsilon, but perhaps exponential in 1 over epsilon. So there are algorithms of this sort for the Euclidean and rectilinear TSP. More bounded ratio. You can always get within the constant ratio of the algorithm. The metric TSP, you can get within a factor of 3 halves using Christofides algorithm. Metric TSP is the edges of the triangle called. Ratio bounded by f of n for a function Gordon. So there are various functions. Asymmetric K setter you can get within log star of n, whatever the size of the problem. Log star is the number of times you have to take log to reduce the number down to 1. Point set width, square log n, log n, log squared n, square root n, polylog n, log, all sorts of things. And so the question is, what is the best type of approximation that can be obtained assuming P equals N? So, for instance, chromatic number. I told you that we're given a graph. We want to assign colors to the vertices so that no two vertices that are endpoints of the same edge get the same color. In our book, we include the proof of an earlier result that shows that if P is not equal to P, you can't get better than factor of 2. Lund and Yannikakis and a bunch of others eventually got to the following result. Unless P equals NP, there's no Polynomial approximation algorithm for chromatic number that, for all instances, guarantees a ratio that for any epsilon can guarantee the ratio number of these to 1 minus epsilon times I. So n vertex graph, you pretty much you can't guarantee better than essentially n times optimal plus, which is really bad. And the proof technique for these results, both our earlier one and Yannikakis, is a gap transformation. So you give it a gap. You give it an instance I of an NP problem A, construct an instance I prime of your problem such that if the answer is yes, then optimal equals k, and if the answer is no, then optimal is greater than some function times k. And if you have a gap, you want to prove, and that's where you get. So starting with the problem with the gap, you can get gaps for other problems too. So for our proof, we used graph products and multicoloring, but that was a baby technique compared to what we have now. The technique that's been used since 1991 is probabilistically checkable proofs. This was started by Rohr and Safra and Rohr and Sudan and Segedin in the early 90s. So what's a probabilistically checkable proof? Or PCP. A PCP for a statement S of length n is a string L and a polynomial which represents the proof. And a polynomial time verification argument given S and a mechanism for assessing specific bits of L are proof computes probabilistically and in finite time reaches conclusion about the truth of the statement S, satisfying it. So you look at you're given a quote proof, and you're not going to look at the whole proof. You're just going to look at a few bits of it, randomly chosen, and there, based on those bits, you can decide do I believe the statement or not. And this is a valid proof if satisfied by the following properties. If S is true, the verifier always concludes yes, it's true. And if it's false, the verifier says true with probably less than 1/4. So there's no proof that will convince you with probably greater. If it's false, there's just no proof that will convince you with greater than that probability. Define PCP of FG to be the set of decision problems with proof lengths and verifier running proof length polynomial and verifier running time polynomial bounded n, for which the verifier uses only proportional to f of n random bits and looks at only proportional to g of n bits of the proof. The random bits are used to choose which bits to look at. And the theorem of AL and SS is that PCP with proportional to a logarithmic number of bits and only a number of random bits that's only logarithmic in the size of the instance, and only a constant number of bits to prove. The things that you can recognize that way are precisely NP. So it's good for you to define NP this way originally, but this is equivalence. And note, and a wide variety of inapproximate results can be proved by using this result and various strengthenings of it, together with their implicit gap theorems, and there's the gap. And so based on that kind of a gap, you can prove hardness of approximation with results for other problems. So an example, set cover. The optimization version is you're given a set X of n elements and a collection C of subsets of X, whose union is all of X. And you want to find the minimum K such that there's a subcollection containing at most K sets that covers everything. For that set cover, there should be a prime C. Sorry, value signs. And in 1974, about that time, contemporaneously and independently, Lobos and I proved that the greedy algorithm guarantees a solution that's within a factor of log n of optimal. Linear Nanococcus, using PCP type results, proved that you couldn't get better than 1/4 log n. So the early result was within the constant factor of the best you could do, assuming NP is not contained in algorithm running time n to the polylog n. So n to the log n and the log squared n in the equivalence. So that's a weaker assumption. FIGA said that proved that no polynomial can guarantee even little better than the greedy algorithm to within a little over log, unless NP is contained in deterministic time n to the log n. And recently, along Marquardt and Safra proved that you couldn't do better than 0.2267 n log n unless P was empty. So they got the assumption back to P versus empty. So question revised again. What is the best type of approximation that can be obtained, assuming plausible hypothesization, not just P does not others? The problem is, at least for surveyors, that there are a whole heck of a lot of hypotheses people use, which leads to problems. If I ever were to revise Gary Johnson, I should probably cover some of these hardness approximation results. But if you ever look at Gary Johnson, we give the definition of the problem, a reference, and then some comments about related results. A little thing like that. If we were to do it now, this is a page from my column. Here's the problem, and there are the comments. So it's a daunting task to consider trying to do that. So the current big open problem in hardness approximation is the unique gains conjecture. How many people have heard of that? Well, I'll try to quick give a summary of what it is and why it's significant. So we'll start with a problem called label cover, which Lipton and Kakis invented for their paper results about coloring, etc. It's a little involved, but I'll try to illustrate it. You're given a bipartite graph with the two sides of the bipartition being B1 and B2, and a positive integer nm. And for each edge, we have a map from the integers from 1 to m to the integers from 1 to n, which we're going to assign to the edge. And we're also given a bound B, which is less than the number of edges. So if this is the bipartite graph, then and n equals 3 and n equals 2, then I assign a map from the numbers 1, 2, 3 to the numbers 1, 2 to each of the edges. And then my question is, are there assignments to the vertices where you assign a number from 1 to m to the one to the left and 1 to n to the right, which cover at least edges, where edges cover if the numbers assigned to its endpoints satisfy the mapping. So if I make this assignment, you can check that every one of the edges has its mapping satisfied. 3, 1 is there, 2, 1 is there, 2, 1 is there. So this is one where we satisfy them all. So the question is, can you satisfy so that you cover at least B of the edges? And their theorem was that for any epsilon, there's a constant case of epsilon on, such that it's NP hard to distinguish between a case where there is a labeling that covers all the edges in E, and a case where no labeling covers more than epsilon. So there's a big, big gap there. And you can use that for a lot, and it's used for a lot of hardness approximation results. Unique gains conjecture is a specialization of this. For any epsilon delta between 0 and half, there's a constant k such that for label coverages where m equals n equals k, and all the maps are permutations. since n equals n, every number on the left occurs at both the left and the right. It is NP-hard to distinguish between the case where there's a labeling that covers at least 1 minus delta of the edges, and the case where nothing covers more than epsilon. And the conjecture is that this is NP-hard. Now, if it's NP-hard, then we get some nice conclusions. If it's true, for no epsilon greater than 0, can any polynomial algorithm guarantee a solution to vertex coverage that is less than 2 minus epsilon top unless p equals n? Now, why is that interesting? Well, there's a very trivial algorithm that gets you a factor of 2. You just take a maximal matching. Both endpoints of all the edges of the maximal matching, you're within a factor of 2 of the optimal vertex. But assuming p equals np and not the Unix conjecture, the best lower bound we have is 1.3606 minus epsilon. So there's a big gap if we, based on what we know, but if we add the Unix conjecture, we have a tight gap. And this is not the only problem for which this is true. For vertex cover, max 2 set, we get the same thing. Tight bounds assuming Unix conjecture, but bigger gaps. This is a maximization problem, so the bigger bound. Max cut. And then there's a theorem by Raghvendra that says that for any constraint satisfaction problem whose objective function is to satisfy the maximum number of constraints, there's a simple approximation algorithm based on semi-definite programming which provides the best possible guarantee, assuming both the unique conjecture and p is negative. So if it's true, the world becomes a lot simpler. The bets are all out. If you polled people on this one, you wouldn't get a unanimity. I think as many people suspect it's not true, than suspect it's true. But it's a big deal, and copies won prizes on the basis. My favorite, running out of time here, so I'll give you my favorite open problems about approximation algorithms, just a few. I talked about bin packing, and the question is there a constant b such, we know that, I mentioned before, this log squared optimal. If you could root squared log squared optimal to a constant b, that would be great. We don't know you can do it, but we don't know it's hard even for b equals 1. It's going to be hard to find optimal packing, but finding packing that only uses 1 more bit than optimal, we don't know that that's hard. So this is my favorite problem. I've been working all my career, so I really have to stop. I said the karma card cut optimal plus log squared, and that was recently proved optimal plus log optimal by Rothbus. Got an example problem, a couple for this. Can the metric TSD be approximated to within a constant log of 3 halves? 3 halves is a result of Christophidis in 1976. Nobody's improved on it since then. That gives you 3 halves. The best lower bound, assuming p does not NP, is 220 over 219. So big gap there. The asymmetric TSD, again with a triangle problem. Can we do that with a constant factor? The classic iterative matching algorithm guarantees log n times opt. That was the best for a long time. It's now been reduced to log n over log n times opt. That's still a long gap from that one. Big gap between that and constant. We don't know what the answer is. And the final open question, is any of this relevant in the real world? Remember, NP-Completeness is a concept that is both worst case and asymptotic. And there are various cases where NP-hard problems that people often think are well solved. For instance, satisfiability. There are many applications of satisfiability in fields such as model checking for software verification, etc. And it's claimed that for such real-world instances, even ones of truly huge size, they offer no challenge to modern-day SAP codes. People have codes that run effectively in linear time and resolve things. So does this mean SAT is efficiently solved for all practical purposes? No, it just means that the current applications seem to be really easy instances. No, and even for these circuit verifications, if the circuit involves iterative computations like adders and things like that, it becomes much harder to verify the corresponding satisfiable instances. And I maintain that if you took an instance of clique, which is known to be very hard in practice even for random graphs, and translated into a satisfiable instance by following the transformation, the set solvers would have a big trouble. The other one that is NP hard but surprisingly solvable is the traveling salesman problem. A branch and cut approach based on linear programming to learn terminal lower bounds in the optical length, developed by Applegate, Pixie, Quattell, and Cook, and using 30 years or more of theoretical developments in the math programming community, plus a very good data structures heuristics from computer science, can solve surprisingly large instances quickly, 2,000 and more cities. And it finds optimal towards improved optimality in reasonable time for things up to that size. 20 years ago when I was at a workshop at TSP and somebody claimed that it might be able to solve 1,000 city instances, I couldn't believe it. That would ever happen. But using, take instances of random points in the unit square, I read Concord on these on 10,000 different 1,000 city instances. And the running times range from 7 seconds to 38 hours that we solved them all. This is a logarithmic scale. The running times seem to be logarithmic. But even this is not going to be evidence that P equals NP because it runs based on experiment by Hus and Stutzman who estimate the median running time. It's easy to estimate the median running time. You can run very large instances if you have enough processors. 100 processors, you run 100 things in parallel and it stops when it's finished, and you've got the median. And they estimated the running time was exponential square root of x. And that, although 4,500 cities a week is 96 hours. So even the TSP, which has very good practical codes, it doesn't look like we're really anywhere close to solving the problem in time. So to conclude, proving NP-complete results is still worthwhile, although you can still hope for special cases that avoid the hardness or exponential time algorithms that's still fast enough to handle this as you care about, or fast algorithms that get good enough results in practice, if not in theory. And I'll include the photo credits because I had to ask permission for some of those pictures. Any questions? Yes.
So this question probably has a well-known answer, but are we aware of any problems, NP-complete problems, that can be solved in sub-exponential time, say 2 to the square root of n, like this problem? And
what do you mean by sub-exponential?
Like 2 to the square root of n, and where any reduction to this problem blows up the instance by a quadratic, at least.
Well, you can blow up the size of an instance so that exponential time looks like 2 to the square root of n. So you can come up with a problem that has a lot of redundant information, and therefore an exponential time, a previous exponential time now takes 2 to the square root of n. So I can construct such problems. I don't know of any well, take it back. If you take the traveling salesman problem for points in the plane, that's NP hard, and there is a 2 to the square, and there's a 2 to the square root of n now. Okay.
Just want to mention that just when you talk about 2 to the square root of n, for example, unique games, they found this 2 to the square root of n algorithm, but again, that doesn't show it can't be NP-complete.
So I view exponential time as 2 to n to some polynomial to some power greater than 0. Although one of the one of the conjectures that people make hardest results is that satisfiability cannot be solved in time 2 to the little o of n.
That's ETH.